Hello, my name is Jeonghwan from Queen's University Belfast. I'm going to present our work, hard label-based small query black box adversarial attack. I'll tell you the motivation of our work first. The black box adversarial attack is widely considered to be a practical adversarial attack method, but it has a known issue that it suffers from impractical number of queries required to achieve a successful attack. So the motivation is to introduce a novel approach to improve query efficiency of black box adversarial attack. Adversarial attack is a method to generate adversarial examples which are deliberately designed to cause a target model to make a false behavior in its designated task despite resembling a valid input to human. And it has two different settings. In white box setting, the attack method has a full access to the model's architecture and information, which includes the gradient, parameters, and training data set. But in black box settings, the target method can only monitor the input examples and corresponding output information from the target model. Adversarial transferability is the phenomenon whereby adversarial examples which can achieve a successful attack to a model can fool on other models, even if their architectures and parameters are vastly different from each other. The attack methods in the black box adversarial attack setting have no or limited access to the target model, but they are allowed to monitor input and output of the model. The attack strategies can be categorized into three subsets. The first one is transfer-based strategy. In this strategy, substitute model is trained to generate adversarial example to be directly used to attack the target model. In software label-based strategy, it is the query-based approach where the attack method can access input example and the probabilities of target model's prediction. The hard label-based strategy is a query-based approach where the attack method is only allowed to access input example and the class of target model's prediction. Soft label and hard label attack strategies need to approximate the adversarial gradient to conduct attacks. The common approach to approximate gradient is utilizing zeroth-order optimization process. Zeroth-order optimization is a gradient-free optimization that is used for solving optimization problems when gradient-based method is not available. Objective function only permits function evaluations without any gradient evaluations. The generic form of zeroth-order optimization looks like this. But this form is only suitable for soft label-based optimization as it requires the access to the prediction probability. Hard label-based black box adversarial attack setting is considered to be the most challenging as the minimum access to the model is given, such as input example and predicted class. Objective function is observed as the heaviside step function as no access to the prediction probability is allowed. So the zeroth-order optimization of hard label-based black box adversarial attack setting is formed differently from soft label-based adversarial attack setting. The zeroth-order optimization requires many queries to estimate a gradient in every iteration. To address this drawback, an approach utilizes the adversarial transferability between white box surrogate model and query-based black box target model is introduced in many works. The surrogate model is used to guide gradient estimation in the black box attack settings, but most of state-of-the-art which take this approach are soft label based, take the full advantage of zeroth order optimization. The transferability of gradients generated from the white box attack on surrogate model is mitigated when the decision boundary of the surrogate model does not closely match the target model. So the estimated gradient from surrogate model shall satisfy the following requirements. The first one is optimal direction of an estimated gradient is orthogonal to the vector between input example and current intermediate adversarial example. And second requirement is transported example is still adversarial. To find a gradient meets the requirements, the proposed approach generates multiple gradients using utilized white box attack method. Multiple gradients are generated from surrogate model with the examples on the vector between input example and current intermediate adversarial example. It is observed that any gradient generated with the type of examples become near orthogonal to vector V if the distance from input example X is greater than 20% of magnitude of vector V. So using this observation, we introduce a small query black box adversarial attack. The proposed approach begins with an initial adversarial example, and in early iterations, it solely uses the gradient estimated from a surrogate model, and gradually moves to the gradient estimated from black box zeroth order optimization. As adversarial examples are well optimized by estimation from surrogate model, the zeroth order optimization doesn't need many queries to estimate gradient. Therefore, query efficiency is achieved. We first carried out experimental tests on CIFAR-10 dataset. It can be observed regardless target model and utilized surrogate models. The proposed approach outperforms all other benchmark attack methods, achieving around 4 or 5 times higher attack success rate, especially at small query budgets such as 100 and 250. The same results are also observed from ImageNet dataset. The proposed approach will outperform benchmark attack method across all attack budgets. So finally, the conclusion is a novel transfer-based iterative gradient estimation is proposed to guide gradient direction in the black box attack settings. And we designed a hard label-based black box attack method, so-called SCUBA, which has an optimization process guided by the proposed transfer-based gradient estimation. Through the experiment, the improved query efficiency of SCUBA attack method is demonstrated in comparison with several state-of-the-art hard label-based black box attack method. That is end of presentation. Thanks.